Welcome to the Masterclass, everyone. I am absolutely thrilled to have you here today. Okay, we are jumping right into this explainer on what is, without a doubt, the single most crucial molecule in the known universe. I mean, think about it. We interact with it every single day. We're literally mostly made of it, and yet we rarely stop to appreciate the absolute chemical genius of water. So today, we're going to unpack the elegant, life-saving chemistry of H2O. I really want you to treat this like a true masterclass. We're going to define the key terms, explore some mind-bending exceptions to the rules of normal chemistry, and uncover exactly how this one deceptively simple little molecule dictates the existence of all life.
Now, to truly appreciate our subject, we need to start way out with a macro perspective. Just look at this stunning shot of Earth, our blue planet. 3/4 of the surface is covered by water, but you know what's truly profound? Our biological history. Life actually began in water, and it evolved there for a staggering 3 billion years before any living thing ever took a brave step onto dry land. You, me, and all the organisms we know and love are essentially just walking vessels of water, living in an environment completely dominated by it. It's the substance that makes our existence possible.
Here is our roadmap for today's lecture. We're going to start with the magic of water at a microscopic level, move on to its 4 life-saving properties, break down the chemistry of pH, examine a threat to oceans, and finally, we'll look for life beyond Earth. Let's conquer this journey together.
Chapter 1. The Magic of Water. Let's zoom all the way in on H2O to see where this magic actually begins.
Every good masterclass relies on a solid vocabulary, right? So let's define our very first core concept, the polar molecule. A polar molecule is simply a molecule with an uneven distribution of overall charge, which means it has oppositely charged regions. You can think of it a bit like a tiny magnet with a north and south pole. In the case of water, the oxygen atom is highly electronegative. Basically, it's an electron hog. It pulls the shared electrons closer to itself, pulling them away from the 2 little hydrogen atoms. And this unequal sharing, that is the foundational secret to literally everything water does.
So let's visualize that polarity in action. Notice that distinct V shape of the molecule. Because oxygen is hogging those negatively charged electrons, the oxygen end of the molecule gets a partial negative charge, while the hydrogen ends get a partial positive charge. And as we know, opposite charges attract. So the positively charged hydrogen of one water molecule is instinctively drawn to the negatively charged oxygen of a neighboring molecule. This attraction forms what we call a hydrogen bond. Now, these bonds are fragile. They form, break, and reform trillions of times a second, but together they create an incredibly strong invisible network.
Chapter 2. 4 life-saving properties. Let's see how this continuous, invisible dance of hydrogen bonding makes our entire planet habitable.
Here they are, the 4 main pillars of Earth's suitability for life. We've got the cohesion of water molecules, the moderation of temperature, the floating of ice on liquid water, and water as the universal solvent of life. We're going to tackle each of these brilliantly clever chemical phenomena right now.
First up, let's lock down the definitions for cohesion and adhesion. Cohesion is the phenomenon where hydrogen bonds hold a substance together. Simply put, it's water molecules clinging tightly to other water molecules. Adhesion, on the other hand, is the clinging of one substance to an entirely different substance. These unseen chemical forces are doing some incredible heavy lifting in biology, and I'll show you exactly how.
This brilliantly illustrates those definitions out in the real world. On the left, we're looking at water transport inside a plant. As water evaporates from the leaves, hydrogen bonds cause the leaving water molecules to literally tug on the molecules further down. This cohesion pulls a microscopic column of water hundreds of feet up a giant tree, completely fighting gravity. Meanwhile, adhesion helps the water stick to the plant's cell walls so it doesn't just fall right back down. Then, on the right, we have a spider walking perfectly on water. This is surface tension, which is a direct result of cohesion. The water molecules at the surface bond to one another, creating this invisible, trampoline-like film. 2 totally different biological marvels, both powered by the exact same hydrogen bonds. Pretty amazing, right?
Now let me ask you a quick question. Think about most materials in the universe. What usually happens to liquids when they get incredibly cold and freeze into a solid? Typically, as things cool down, the molecules slow down and pack tightly together. The material shrinks and becomes much denser. But water? Well, water has a very different plan.
Water is the grand exception to the rule. Unlike almost every other material on Earth that contracts, water actually expands when it solidifies.
I want you to really let that sink in for a second. It is an exotic, absolute lifesaver of a quirk. If water behaved like normal liquids, our world would be a dead, frozen wasteland right now.
Look closely at the crystalline lattice of ice here. As the temperature drops to 0 degrees Celsius, the molecules are moving too slowly to break their hydrogen bonds. So instead, they lock into this spacious, three-dimensional crystal. These hydrogen bonds actually push the molecules further apart than they normally are in liquid water. Because there are fewer molecules taking up the same amount of space, ice becomes about 10% less dense than liquid water. That means ice floats. When a deep body of water cools down, this floating ice acts as an incredible insulating barrier, preventing the liquid below from freezing solid and protecting all the fragile marine life beneath it.
Moving on to our fourth property, which makes water the solvent of life. Because water molecules are so highly polar, they are perfectly designed to pull apart other compounds. Look at this grain of table salt, sodium chloride. The positively charged hydrogen ends of the water molecules are highly attracted to the negative chloride ions, while the negatively charged oxygen ends rush right toward the positive sodium ions. They totally surround each ion, forming what we call a hydration shell, completely shielding and separating them. This makes water an unbelievably versatile solvent, allowing our blood, plant sap, and really every living cell to carry the dissolved nutrients we absolutely require for survival. All right. Chapter 3, the chemistry of pH. We've seen water stick together, and we've seen it pull other things apart. Now, let's investigate what happens when water molecules themselves pull apart.
So, occasionally, a hydrogen atom in a hydrogen bond between two water molecules will shift completely from one molecule to the other. When this happens, it leaves its electron behind, becoming a positively charged hydrogen ion, while the molecule that lost it becomes a negatively charged hydroxide ion. Now, this is perfectly balanced in pure water, but enter acids and bases. An acid is a substance that increases the hydrogen ion concentration of a solution. A base is a substance that reduces that hydrogen ion concentration. And this delicate microscopic balance, it's vital for every living cell. To measure all of this, biologists use the pH scale, which compresses the massive range of possible concentrations using a logarithm. Notice how the scale ranges from 0 to 14. Pure water sits right there in the middle at a completely neutral 7. But because it's a logarithmic scale, each single unit represents a tenfold difference. That means a solution at pH 3 isn't just twice as acidic as pH 6. No, it is 1,000 times more acidic. The scale covers everything from highly acidic battery acid and lemon juice near the bottom, all the way up to incredibly basic household bleach and oven cleaner at the top.
Ultimately, the type of solution we're dealing with is entirely determined by this chemical tug-of-war. In an acidic solution, the balance tips to having more hydrogen ions than hydroxide ions. In a neutral solution, like pure water, they are exactly equal. And in a basic solution, there are more hydroxide ions than hydrogen ions. Living organisms are incredibly sensitive to these shifts. Just to put it in perspective, the pH of human blood has to strictly hover around a very precise 7.4 just to keep us alive.
Chapter 4, a threat to oceans. Let's step out of the lab for a moment and examine how these invisible pH changes have massive, real-world consequences for our planet's delicate ecosystems. We need to talk about ocean acidification. By definition, this is the lowering of ocean pH due to the absorption of excess human-generated carbon dioxide. Right now, about 25% of the carbon dioxide released into the atmosphere by fossil fuels is being absorbed by the world's oceans. And while that does reduce atmospheric CO2, it simultaneously kicks off a series of chemical reactions in the water that researchers are monitoring very, very closely. Let's impartially trace this exact chemical reaction. When carbon dioxide dissolves in the ocean, it reacts with the water molecules to form carbonic acid. This acid then dissociates, releasing hydrogen ions. Remember our rule about pH? More hydrogen ions mean a more acidic solution, which lowers the ocean's overall pH. But the secondary reaction here is just as crucial. Those extra hydrogen ions combine with naturally occurring carbonate ions. The issue is that marine organisms like reef-building corals desperately need those carbonate ions to build their calcium carbonate shells and structures. So, by locking up the available carbonate, ocean acidification threatens the very foundation of coral reef ecosystems. It is pure cause and effect chemistry playing out on a planetary scale.
For our final chapter, Chapter 5, let's zoom out. way out, from Earth's oceans to the breathtaking possibilities within our entire solar system and beyond.
Astrobiologists, the scientists actively looking for life elsewhere in the universe, always follow a very simple mantra: follow the water. Because of water's extraordinary properties as an insulator, a solvent, and a temperature moderator, it is the ultimate cosmic prerequisite for life as we know it. Just look at this digitally treated photograph from the Mars Reconnaissance Orbiter. Those dark streaks running downhill on the Martian surface provide evidence of hydrated salts, which strongly indicates the presence of liquid water. Finding this tells us that the necessary chemical stage for life might just exist right next door in our very own solar system.
I want to leave you with this final thought. Today, we've seen how 2 hydrogens and 1 oxygen atom come together to create a polar magnet that literally defies gravity in trees, expands when frozen to protect whole oceans, and dissolves the nutrients completely necessary for our blood. If this single deceptively simple molecule is the absolute foundation of our entire biological existence, what incredible secrets might it be holding on a planet millions of miles away? Keep asking questions, keep studying the natural structures all around you, and never, ever lose your sense of wonder for the chemistry of the universe. Thank you so much for joining me in this explainer.